Have you ever wondered how a chair, something so simple, so ordinary, actually works? We sit down, shift around, maybe lean back, and never really think about it. But behind every chair is a world of physics, engineering, and biomechanics, all working together to keep us comfortable, balanced, and safe. Let's break it down. The moment you sit on a chair, your body exerts a downward force due to gravity. This force, known as your weight, W equals mg, where m is your mass and g is the acceleration due to gravity, which is 9.81 meter s square. The weight must be properly distributed so the chair doesn't collapse. A well-engineered chair ensures that this weight is spread evenly across its structure. The seat acts as a load distributor, taking the force from your body and transferring it to the legs of the chair. Each leg experiences a portion of the total force, usually 1/4 of your weight in a four-legged chair, assuming perfect weight distribution. If the chair is poorly designed and has weak joints, stress concentration can cause failure at critical points, often where the legs connect to the seat. In material science, the stress is defined as sigma equals to F over A, where F is the force applied and A is the cross-sectional area of the material. Chairs are designed to minimize stress by using strong material or increasing the contact area. Ever lean back in a chair and almost tip over? That's because of the center of mass shifting beyond the chair base of support. The center of mass is the average location of all the mass in an object. In a person sitting, it's typically just above the pelvis. The base of the support is the area between the chair's leg. A wider base means more stability. The rule of thumb in physics is that if the vertical projection of the center of mass fall outside the base of support, the object or person will usually tip over. To prevent tipping, chairs are designed with leg positioned outwards to widen the base of support. The backrest and seat angles are calculated to keep the user's center of mass within a safe range. Rocking chairs and recliners usually use curved or extended base to dynamically shift the center of mass safely. Different materials also behave differently under stress. Wooden chairs rely on compressive strength, resistant to being squeezed, and tensile strength, resistant to being pulled apart. Joints are often the weakest point, so glue, screws, or dowels reinforce them. Metal chairs are often made of aluminum or steel, which have high yield strength, the point where they permanently deform under stress. Tubular metal structure maximize strength while minimizing weight. Plastic chairs use polypropylene or polycarbonate, which distribute stress evenly due to their flexible yet durable nature. Injection molding allows for complex shape that eliminate weak points. A fun engineering trick, the cantilever chair, such as the famous Seska chair, has no back legs and instead uses the bending strength of a steel frame to support weight. This works due to the concept of beam bending, where the material resists deformation by distributing the force through its shape. A chair job isn't just to support weight, it also needs to fit the human body. That's where ergonomics comes in. Seat height. Ideally, the seat height is about 18 inches, 45 cm, allowing a person feet to rest flat on the ground with knee at a 90-degree angle. If the seat is too high, it reduces blood circulation to the leg. Backrest angle. The human spine has a natural S-curve, so backrests are designed to follow this shape. A typical office chair has a 100 to 110 degree recline, which reduces spinal pressure. Seat cushioning. Too much softness can cause bottoming out, concentrating pressure on the pelvis. Too much firmness can create pressure points, leading to discomfort. That's why high-end office chairs use memory foam, which conforms to the body while maintaining structural integrity. Some even have mesh design which distribute weight while allowing airflow to prevent overheating. Ever notice how modern chairs, office chairs, adjust height, recline, and even tilt with ease? That's because of smart mechanical system. There is the gas lift mechanism where you pull a lever to adjust height. You're activating a pneumatic piston filled with compressed gas. This gas expands or contracts, raising or lowering the seat. Reclining mechanism. High-end chairs have synchro-tilt system which adjusts the angle of the seat and backrest at the same time, keeping your posture natural. Weight-based recline. Some chairs automatically adjust their tilt tension based on the user weight using torsion spring or hydraulic dampers. The goal? Reduce muscle strain while allowing micro movements that prevent stiffness during long sitting periods. Some modern chairs challenge traditional concepts with radical engineering. Kneeling chair. Instead of a backrest, these use a tilted seat that shifts weight forward, promoting spinal alignment. Zero gravity recliner. Inspired by NASA, this chair distributes body weight evenly, reducing spinal compression. Active sitting chair. Some stools have a convex base, forcing slight movement that engage core muscle, preventing stiffness. At first glance, a chair might seem simple, but when you break it down, it's an incredible blend of physics, material science, and design. From the moment you sit down, forces are at play, balancing weight, ensuring stability, and keeping you comfortable. So next time you take a seat, remember, you're saving the world. Nah, I'm just kidding. You're not just sitting on a piece of furniture. You're experiencing a masterpiece of engineering, built with precision and design to support you in ways you never even realize.